Everybody. In this video, we're going to talk about linear functions. So the reason why they're called linear functions is because if you are to graph the inputs and outputs of a linear function on a coordinate plane, they form a straight line. So in this particular linear function, this point right here represents an input of 0 and an output of 5. This point right here represents an input of 3 and an output of 3. And this input, or this point right here, represents an input of 6 and an output of 1. And in this particular linear function, we have a decreasing pattern because the outputs are decreasing with each input. And if you notice, what they're decreasing by is consistent. We're consistently subtracting 2 to get from each output to the next one. And this pattern is what makes it linear. So all linear functions are going to have consistent patterns of either adding or subtracting a consistent amount. So in our example of the penny jars, where we have a penny jar that starts with 2 pennies, and each day you add 3, this would be an example of a linear function because you're consistently adding 3 pennies every day. And if we wanted to figure out how many pennies are in the jar on day whatever, we could represent this with a table if we wanted to. So we could say, we'll have one column for our input, which is usually represented on the x-axis, and then one column for our output, which is usually represented on the y-axis. And we can say on day 0, we have 2 pennies because that's our starting amount. And then on day 1, we have 5 pennies because we added 3 pennies from day 0. And then the next day, we'll add another 3 pennies, which gives us 8 pennies on day 2. And on day 3, we would add another 3 pennies, and that would give us 11. And on day 4, you'd add another 3 pennies, and so on and so forth. So on day 4, we would have 14 pennies. And so if we wanted to figure out the number of pennies that are on day n, or if you wanted to, you could even use the variable x. What you would need to do is you'd need to say, okay, well, how many times have I added 3 to get to day n? Well, since on day 1, I had only added 3 once, and on day 2, I added 3 twice, it looks like the number of times that I would add 3 would just be n times. And since repeatedly adding 3 n times is the same thing as multiplying 3 by n, I could think about this as 3 times n. However, this formula isn't complete because if I tested it out and I said, oh, if n equals 0, does that give me 2? Well, no, because plugging in 0 and doing 3 times 0 does not give me 2. And if I plug in a 1 times 3 does not give me 5. But I can adjust my equation by adding 2 to this, and then it would work because 3 times 0 plus 2 does equal 2, and 1 times 3 equals 3, plus 2 would give me 5, and 3 times 2 is 6, plus 2 will give me 8. And so this would be the formula for how many pennies I would have on day n. And I could write this as a function rule if I wanted to, and I could say the function with an input of x is going to equal 3 times the input. So I'm switching variables here, but you could use an n instead of an x, and that would be fine. But you do 3 times your input, and you add 2. So the output when you input an x equals 3 times the input that you're putting in, which is the x, plus 2. And this is an example of a linear function equation that describes the rule that we're seeing. And if we were to graph this situation, we would see that it really is a linear function in the sense that it makes a straight line. Because on day 0, we had 2 pennies. On day 1, we had 5 pennies. On day 2, we had 8 pennies. And on day 3, we had 11. And you could keep graphing if this graph had continued further, but we would have a straight line that looks like this. And so that's what makes this a linear function. We can also have linear functions, though, where we have a decreasing line. Like, for example, if Jill has $400 and she spends 20 each day, how much money does she have on day blank? We could again make a table to represent this, and we could say, okay, the X is usually represented by the input, the Y is represented by the output, and in this case, the input would be which day number it is, and the output would be how much money you have. So on day 0, we have $400. On day 1, if she's spent $20, we would subtract 20, which tells us that she has $380. On day 2, we would subtract 20 again, which would give us $360. On day 3, we would subtract 20 again, which would give $340, and so on and so forth. So if we wanted to figure out how much money she has on day N, we would say, okay, well, it looks like you just subtract 20 N times, which we can write as negative 20 N. And since she started with $400, we would also need to add 400. And you could also rearrange this equation and write it as 400 minus 20n times. And that might make more sense in the context of this problem. But the two equations would be equivalent regardless. And so the function rule for this situation would be that the output, when you input an x, equals negative 20 times x plus 400, where the f of x, or the output when you input an x, represents the amount of money that you have, and the input, or the x value, represents the day number that you would be on. So sometimes you can have a subtracting pattern or an adding pattern, but in either case, if you're adding or subtracting the same amount consistently, then you're going to have a linear function. And one of the common ways that linear functions are represented in equation form is called slope-intercept form. You probably have heard of this in previous algebra classes. And basically what the idea of slope-intercept form is that the b value, or the number that's added to the end of the equation, is your starting value. And the number that's multiplied by your independent variable is the rate that you're consistently adding or that you're consistently subtracting. So in our penny jar example, we had f of x equals 3x plus 2, because we started with 2 pennies and then we added 3 pennies for each consecutive day. In the example where she was spending her money, and we had f of x equals negative 20x plus 400, the positive 400 represented that she started with $400, and the negative 20 showed that she was consistently subtracting $20 every day. So that's the basic idea of a linear function. And you likely won't teach slope-intercept form to your students because this is usually taught in middle school. However, it is helpful if you can start introducing the concepts of linear functions to your younger students, so that when they get to middle school and they write out these equations, they have a history of contextual understanding for how linear functions work. So you'll see some examples in the case studies of how this would look, and how you can introduce a linear function concept to the students without actually teaching them the equations for representing those patterns. Um, so I hope you guys enjoy those in the case studies. And if you have any questions about linear functions, please let me know.